We're going to start with the very beginning, so we might as well start about fiber and a little bit about how it got started. Well, it began in the 70s with Bell Labs, and the first installation was done near where I live. I live in Chicago, in St. Louis, but just north of us, by AT&T in 76. So that's quite a while ago. And of course, through the whole 80s, fiber optic continued to grow. I've been in the communications connectivity business since the early 80s. So I've been with fiber a long time. Single mode actually came out in the 80s as well. And when we moved to single mode fiber, we were able to get more bandwidth, longer distances, and it's a lot less expensive than copper. If any of you remember the days of planting big cable in the ground with thousands of pairs, you really know the difference between copper and fiber. And we're in the day of fiber right now. So in the 90s, we ended up with transoceanic fiber, where we actually replaced copper cable that went under the ocean, and we replaced it with fiber. And that work continues as the need for the network to expand and grow continues to occur. And then the 90s brought us a lot of opportunity. Of course, it brought us cell phones, the internet, and cable. And cable TV and broadband with fiber is extremely popular. And that's one of the drivers for the business for sure. But also today, we talk about prolific networks that we have. The enterprise fiber business is huge, and it continues to grow. We hear a lot about it when we talk about hyperscale data centers and things like that, but there's still many private companies that have their own data centers. There's still a need for data center type work, especially when we're talking about building backhaul networks for the new 5G networks that are coming along. Old central offices are turning into data centers. The huts underneath some cell towers are turning into small data centers. So this need for continued use of fiber in our networks continues to expand. There's a lot of benefits for fiber. We know most of these, but I'll go over them a little bit. First one's long distance. You can go a long way with fiber. We're talking about kilometers we can go with fiber. So it goes a long way. A lot more capacity, higher bandwidth. A big one is there's no EMI or electromechanical interference or radio frequency interference. There's no EMI, RFI, this electromagnetic interference. It doesn't affect the glass. The fiber optic works with pulses of light, and we're not sending electrons down the line. We're sending light pulses down the line. It makes it hard to tap, so it is secure. Can you tap fiber optics? The answer is yes. Is it practical? Probably not. And trying to do it, you will really create an incident. But it's difficult to do. Now, I indicated here that since we don't have any electrical going into fiber, there's no shock and grounding. But we have to put this disclaimer down here. If you have armored fiber, if there is a metallic component to your fiber, most common is the armoring around a fiber cable, that would be conductive. So you have to pay attention to that from a grounding perspective. It's a lot smaller than copper. We can replace a lot of copper cables with a single fiber, and it's independent of applications. We can do all kinds of things on fiber that the same things we can do on copper, and probably even more.
Carl, we got a good question. What about surge protection?
I don't know about light surges. That would be, I've never heard of that. That's a good question. The electronics that drive the fiber solutions, in other words, we need electronics to create the pulses of light that we push across the cable. Those electronics that are on either end of the fiber cable, there's probably a need for some type of protection to prevent surges and things like that. So that would be the answer I would give, Chris. Do you have any comment more on that?
No, I think that's right. I think the main thing is the safety, grounding and bonding for safety if you have metallic members in the cable. Otherwise, you're following surge protection for the electronics back at where they're mounted.
Yeah. So here's a little schematic up on the screen here that kind of shows what a fiber circuit would look like. The yellow bar in the middle represents the fiber optic cable, and that cable is attached to a component called a transceiver, an optical transmitter / receiver. It does both functions. It receives a signal and it transmits a signal. In the old days, that transceiver was built inside the electronics. So the little pink boxes would move into the gray box A and the gray box B, and it would be an internal component to the networking products or networking equipment that we had. The transceiver was internal to that. But in recent times, that's changed, where we've made the optical connection remote from the electronic equipment, and we've standardized the connections on the electronic equipment, so we can put different types of transceivers in there. So you just plug the transceiver into your electronic equipment. Again, the transceiver then will take the optical signal and turn it into an electrical signal that can be handled by the electronic equipment, and vice versa. The electrical equipment will turn, the transceiver will turn that signal into an optical signal that we can send across the fiber optic cable. So that's this chart right here, as simple as it looks. That's pretty much it. I mean, it gets a little bit different when we start talking about the different types of components and the different types of transceivers, et cetera, the different types of optical fiber. But basically, this is what the circuit looks like. When we take a look at the cable itself, the actual fiber, let's not talk about the cable. Let's just talk about, in terms of copper, let's talk about the conductor. So in an optical fiber cable, the conductor is a piece of glass, a glass thread, so to speak, a glass fiber. And the glass fiber has three components to it. It has what's known as a core, and the core in the fiber is made out of glass. It's glass, and that's the primary pathway for that optical signal to go down to glass. At the same time the core is constructed, the cladding is constructed, and the cladding is also glass. It's also glass, but it's a little bit different in terms of glass, where that junction goes between the glass cladding and the glass core. That junction, where those two glass elements come together, become very important, and we'll talk about that in just a moment. And there's several ways this is made. I encourage you to go up to YouTube and look at some of the videos that are up there on how fiber optic cable is made. They're fairly interesting. There's two processes. One's called outside deprivation and one's called inside deprivation. That's not a big deal, except that we start with a glass blank of very, very, very pure glass. Now, I've been to where they make fiber optic cable, and I've looked at a glass blank. I think Chris has. And
now it's the time.
Somebody's needs to mute themselves.
Please mute. Thank you.
See, you can put a postage stamp, was the example I saw, at the end of a glass rod, solid glass rod that was probably 50, 75 feet long. I don't know how long it was. It was pretty long, but that postage stamp was crystal clear when you look from one end of the glass to the other. You can't do that with what window glass is made out of. This is very, very pure silicon glass, and the process puts two pieces of glass together, so to speak, if we want to say it that way. We surround a glass core with a glass cladding. And then to protect that glass, we put a coating of plastic around it. So it's there's a plastic coating around the fiber itself. The fiber consists of the core and the cladding, and then the coating goes around the fiber. What that does, it turns the diameter of the fiber then into 250 microns. You'll see that on the left. So the fiber diameter ends up being, with all three components, the core, the clad, and the coating, ends up being 250 microns. So another way to look at this is this way. If we look at on the left, we'll see multimode fiber. The black circle represents the core and the cladding, and the gray represents the coating, the plastic coatings on the outside of it. So we know that 62.5 fiber, 125 microns is the diameter with the plastic coating on it. The same with 50 micron. 50 micron fiber becomes the outer diameter is the same as 62.5. It becomes 125 microns. And the same with single mode. A 9 micron fiber, when the plastic coating is put on it, all of these fibers then become 125 microns. So with the outer plastic coated, including the diameters on all of these different fiber types are all the same diameter, including the plastic coating. Now, when you prepare your fiber to connectorize it in certain cases, then you'll have to use a special tool to scrape that plastic coating off of that fiber. But when it comes right off the factory and in a spool and you're ready to make it into a cable, all the elements, the glass elements here, are all 125 microns. Now,
hey, Carl, we've got a question related to that. So this comes from Josh Varhala. Is it the cladding or coating that protects against refraction?
Well, we're going to talk about that right now. That's a great segue.
I've got another question as well about SFPs. I think we're going to talk a little bit more in depth about SFPs later in the conversation.
Well, yeah, the SFPs are, he's talking about a transceiver type called an SFP. Yeah. We won't get to that probably until session number 3. So that'll be the 3rd week in October.
Okay.
The 2nd or 3rd week in October, we begin digging into the transceivers, the different types and what they do, and the different Ethernet standards where you use them. But we'll get to that in a couple weeks as we continue down this path of 1 hour a week for 4 weeks.
Okay, so the question is, are all SFPs created equal when talking transmission speed? The answer is they are not created equal, and we'll dive deeper into that in another session.
Yeah.
And so as we get into cladding and coating, another question is, wasn't there a 100 micron fiber once upon a time? And yes. The answer is yes, and I'll let you talk from there, Carl.
Well, there was. It was 100 micron fiber, but that's really, really old. There was an old timer on the session today. Now, whether the 100 micron fiber was coded out to 125 microns, I don't know. I have no idea. But you're right. There was 100 micron fiber back in the day, and there still may be some uses for it in some industries. I just don't know. So I'm going to go back to the question, and it's up on the screen, is about the difference in the core and the cladding. And this comes to a concept known as refraction. So the goal here, if we look at this chart, the core is represented by this green bar. So we try to keep our optical signal inside the core. So we're trying to keep our optical signal inside that green space, and that you can see that the signal, depending on the angle at which it's transmitted into the core, depending on that angle, it will bounce off, for lack of a better words, it will be reflected or refract off of the cladding. That's that light junction. These are two different kinds of glass. The green is the core. That's one kind of glass. And then the other is a glass that's just slightly different than the core. And when the light signal that's being inserted into that fiber reaches that junction between the core and the clad, it will angle off and continue to traverse down the core and reflect itself back and forth until it gets to the other end. Now, some of you may be bow fishermen. So you may stand on the end of your John boat with a bow, and you know where you see the fish, and where the fish actually is in two different spots. That's because of a refraction. The refraction there would be the difference in materials between the Earth's atmosphere and the water. So the gas of the atmosphere and the water, where that junction occurs, the light bends. That's the same principle that happens right here. The glass bend, the image bends, or the object appears as though it's bending when it's moving through the glass. The other example would be, if you want to do this at home, fill up a glass tumbler with water and put a pencil in it. And if you look at that, it looks like the pencil has bent, or it has a bend in it, but it really doesn't. And we know, we pull the pencil out of the water, it's straight, but when you put it in the glass, it appears as though it bends. That same concept of what happens to light. And of course, what you're seeing is the image, the light reflected off of whatever image you're looking at. That light is refracted, and so it changes direction. So let's look at it another different way. We'll look at it another different way in just a second, but just remember that this junction between these two types of glass, the core and the clad, that junction there is very important in order to keep our signal inside the glass, so we can get the maximum amount of signal out of the end of the glass. Did I describe that right, Chris?
Yes, you did. I think
great.
so.
All right, thanks. So the next thing we talk about when you're reading a spec sheet about fiber is we learn about wavelengths. Wavelengths are given to us in a measurement known as nanometers. Now, visible light, as you see on the left, where the colors of the rainbow, red, orange, yellow, green, blue, indigo, and violet, those colors, so to speak, and the variance between each one of those primary colors, that visible light there has a wavelength. So the violet color would be 600 or 360 nanometers, and the red would be 716 nanometers. So those wavelengths are different, and then for each color of glass. Well, the same thing happens when we move up these, when we move up to the infrared area on the scale where it says infrared. We notice that multimode starts at 850 nanometers, which is light, but it's invisible. It's beyond the visible light spectrum that ends at 760 nanometers. And so multimode runs from 850 nanometers to 1300 nanometers, and that's represented by those two orange bars. That shows the how far the signal goes, or how wide the signal is, or the wavelength, 850 to 1350 nanometers. If we go to single mode, it changes. It goes from 1310 to 1550, and it can go as high as 1625 nanometers. So single mode is a little further up the spectrum than multimode is. But that's kind of the difference between multimode and single mode, other than the diameter of the glass, the different of the core. Remember, one is like 8 or 9 microns, and multimode is 50 microns. Other than that difference in the diameter of the glass, the other difference is the wavelengths, where our information is being transmitted on what wavelength on that glass. So we go back to where we were with this refraction. So we need to think about this, about how light travels down that fiber. Light travels down the core. If you take a look at the picture on the top, you'll see single core. On single mode, the light travels pretty much straight through the middle of the glass, because there's only one mode. So light travels on various paths down the glass. And if we go to multimode in the middle chart, you can see here that there are multiple pathways. In this chart, 1, 2, 3, there's 5 of them drawn here, and we can see there's 5 different paths, and that signal will traverse down the fiber, and it will reflect off of the cladding and get to the other end. Now, there's 2 ways of doing this. The bottom is known as stepped index, and what that is a very sharp angle. So depending on the angle that we launch the signal or the light into the core, it'll bounce around and come out at the other side. But you can notice that some of these paths are longer than the others, and some paths are short. So what happens is the signal at the end of the fiber gets there, even though the signal's been broken up into different modes or different paths, it gets there at different times. And we know that signals that get
You're on mute, Carl.
Carl, you're on mute somehow.
Okay, can you hear me?
Yeah, you're back.
All right, I don't know what happened there. So anyway, this stepped index type of transmission, that's gone away. And now what we use is what's known as graded index. So this junction between the core and the clad is not very abrupt. It is gradual. So there's a gradual change. I don't know any other way to describe it. There's a gradual change between the type of glass in the core and the type of the glass in the clad. It's gradual, and it becomes what's known as graded index. So we gradually work our way to the boundary, and then we gradually work our way back. And that junction between the two, if I'm not mistaken, they call that a trough. But whatever, what happens is with graded index multimode fiber, the signal gets to the end of the fiber at about, not exactly, but it gets to the end of the glass all at the same time. So all these signals get down there very close to the same time. So there's a difference between stepped index and graded index. We don't deal much with stepped index at all. Everything that we deal with in the world that we live in is graded index. So if you hear the term graded index, that's what that means. The modes tend to propagate in the middle of the core and arrive at the end at nearly the same time. So that describes that. So the next thing we got to do is how do we launch our signal into the glass? So these pictures on the right represent the core, the bright colors in the middle, and the clad, that would be the other color on the outside of the glass. The core and the clad are represented in these two pictures. And an LED is a light emitting diode, and it emits a light signal into the glass at 850 to 1300 nanometers. Remember that? That's multimode. 850 to 1350 nanometers is the LED, and it emits light in those wavelengths. That's LED. Now that was the early light source for multimode. And there may be still some LED products out there. There might be, I don't know. But what came after LED then was laser, light amplified from the simulated emission radiation, whatever that means. So then the next thing came up was lasers, and lasers had would launch that light in these wavelengths from 1310 nanometers. If you remember that, that's the low end of single mode fiber, all the way up to 1625. And then there's a break between 1550 and 1625. But anyway, it launches it all the way up to the highest end of the spectrum for light with lasers. So lasers can work basically in the single mode range, 1310, which is above multimode. Now, what happened is we needed stronger light emitters in the multimode world, and lasers became very, very expensive. That was number one. And the number two thing is they were very difficult to mount onto printed circuit boards, so we could make miniaturized electronics, so we could make things like transceivers and other things like that. So we needed to come up with a new kind of light emitting source. And so several years ago, back in the day, we came up with which is known as VCSEL, VCSEL, vertical cavity surface emitting laser. And it's a special type of laser, and it operates in the multimode range, 650 to 1300 nanometers, 1300 nanometers, and you'll find VCSELs in this range here, and they work with multimode.
Hey, Carl, we've got a question from Ariel. Which of the multimode fibers is more effective?
Well, we're going to talk about this, but we might as well just spill the beans right now. 50 micron is the standard today. The 62.5 micron multimode fiber has primarily been obsoleted by TIA and other organizations here in the past couple years. 50 micron fiber is the de facto standard for multimode these days. Now that doesn't mean that there isn't 62.5 still out there in the marketplace. Well, it is, because we have to do MAC work, and some legacy systems may still operate on 62.5 multimode fiber, and we need to do MAC work in that area. So you need sources to buy 62.5. So you'll find some of it, but if for new work, it's all going to be 50 micron.
And,
did I answer that correctly?
Yeah, and Scott Agen also had the question or the comment. So when stating laser enhanced for OM3, OM4, and OM5, are they using VCSEL or laser?
I think they're using VCSELs, but I'm not 100% sure. I'm going to pass it to my boss, Chris.
I think it depends on the technology that the application end user is. Very likely for OM3, they're using laser. VCSELs are getting into OM4 and OM5 as they use the enhanced bandwidth of the fiber.
Oh, when they move up to lasers.
The laser enhanced,
okay.
Yeah.
Yep.
So
the answer to that is both, and it depends on the equipment. That's
correct. And Phil also made the comment, a multi and single mode depend on application. That's absolutely true. It's very application specific.
Right. Okay. So let's make our fiber a little bit bigger and let's turn it into a cable. So in order to turn the fiber into a cable, we do what's known as buffering it. So this is one way that we build a cable, is we put a buffer around the cord and the clad. And that buffer is a soft plastic, a soft protective coating. And this is put around the core and the clad. That 250 micron cable then turns into 900 microns. So this is what we were talking about up until just now. And now we've added a buffer to the outside of that. And now we've created a cable like you're used to seeing. Many of you have seen these. Here's some examples of it. This is a simplex, a fiber that's buffered out, and there's only one fiber, so it's simplex. Now we see fibers where we have two fibers underneath a jacket. They're buffered. Each one of these fibers is buffered. I guess the buffering here is represented by this blue at the very end here. That's buffered out and made a duplex cord. We see it this way sometimes in what's known as a zip cord, where you can just kind of rip it apart. And then in distribution cables, another term for that would be a MIC cable. But these distribution cables are tight buffered cables too, primarily. So this is what the buffer does. It's just very soft. It protects the glass and allows you to handle it and work it properly, and allows you to connectorize and do all the things you want to do. And we buffer out to 900 microns. This is a pretty common thing, and it's been around a long time. Now, the other way that we handle that fiber is these individual fibers. Now I'm talking about the fibers that have the cladding. They're all the way out to 250 microns. They have the plastic over the core and the clad. They're put together in what's known as a ribbon, or loose tube. So let's do it at the top first. So each one of those individual fibers is not tight buffered. They're actually at 250 microns, and they're loose inside of a buffer tube. So let's look at the difference. Rather than it being tight buffered, which is right up against the glass like it is here, it's in a tube. So it's in a buffer tube, and it's not really surrounding each one of the individual fiber elements, which is 250 microns. They're loose inside of a buffer tube, therefore the word loose tube. So why do we have loose tube fiber? Primarily loose tube fiber was designed so it could operate in environments where it may get rather cold or rather warm. So think about an aerial fiber cable, one that goes from pole to pole and it's exposed to the sun. Or let's think about one that's in the ground and it may be exposed to winter. And what happens is it gets cold. Well, what happens when things get cold? They shrink. And what happens when things get warm? They expand. So what happened is the fiber optic people invented a way that they could make the jacket of the cable expand and contract based upon the environment. But the fiber was kind of bunched up in here a little bit. Not a lot, but bunched in there a little bit. It didn't take a straight path and it wasn't very tight, but it actually was curved and bent down through the tube. So if it got cold, the jacket and the fiber could shrink together and the fiber would still be inside that tube and operate, or it could get warm and the jacket could stretch out a little bit and the fiber would not break. So the point of having tight buffers is to prevent, or a loose tube is to prevent the fibers from breaking due to environmental conditions that would either shrink the jacket or expand the jacket. Does that make sense? I hope it does to everybody.
It does, Carl, and we've got a couple of comments here. One, are the characteristics of tight buffer nearly the same now? And to answer that, I would say yes. I mean, the manufacturers should standardize on the 900 micron strippability, and that kind of thing will certainly vary, but everybody's competing to have the same level of strippability, and geometrically should be all identical these days. Would you agree?
I would agree with that.
And another comment, when purchasing an SFP, the light source, the transceivers at the end, they've never needed to question whether they needed LED, laser, or VCSEL. You just match the SFP to the fiber type. Isn't that correct?
Well, yeah, when you buy the transceiver, it's aligned up with a certain Ethernet standard, and that Ethernet standard, and we'll look at this very closely in some other classes, will line up to certain types of transceivers for certain applications based on the Ethernet standard we are. Are we at 10 gig? Are we at 100 gig? We at 400 gig, 800 gig? Those kinds of things. They're going to change. They're going to change the type of SFP you would use, and we would do it by and make sure we order the right one. There's also some electronic stuff that goes on within transceivers that compresses and handles the signals a little bit differently based on the different Ethernet standards. So an SFP is maybe just too much of a generic term. We're more specific with transceivers than just the first three letters these days.
Yeah, and one other comment is all OSP fiber usually loose tube, and I'll answer that one if you like, yep. Carl. Currently in the market, and traditionally over the years, loose tube was predominant. Over the last 5 to 6 years, ribbon has become bigger and bigger as the backbone product is requiring higher fiber counts, higher fiber density, and mass fusion splicing, which works really well in the trunk and backbone segments so that they can go in and splice the cable in quicker and that kind of thing. Overall, loose tube versus ribbon, loose tube seems to have the edge by about 2 or 3% all the time these days, but it's almost equal in terms of deployment.
Well, just to be in the outside plant world, you could have loose tube cable. The ribbon cable still sits inside of a loose tube. And there's a picture of it on the slide here on the lower left where the ribbons are stacked on each other.
Okay, maybe I misunderstood the question. It's always, I think it's always in a loose tube format. You're correct.
Right. Now, what happens with the ribbon cable is each of the 250 micron elements are dyed a different color. So that plastic coating on the outside of it is dyed a different color so that you can tell one fiber from the other at both ends of a single ribbon. That's one thing that happens. And the second thing that happens, there's a little bit of adhesive, just a little bit, between each one of these fiber segments so that they're connected together and they come off and they feel like one strip. It's like a piece of tape. It's like a piece of ribbon. And so they're connected together like a ribbon, each of the individual fibers. And they're kind of, they're kind of attached to each other. And each one of the individual segments is its own color, so you can keep track of them. So when they get into the bundle, if I'm working on the blue one on one end, I'm working on the blue one at the other end. Or if I'm working on the red one at one end, I want to get the red one on the other end. So that's why they're color coded. We'll get into that a little bit too. But this is pretty much standardized from all manufacturers on the construction. Now, what Chris was talking about is we can take these ribbons then and we can stack them together in bundles. And if you look at the bottom lower left, you'll see these ribbons are now stacked on top of each other. And now we can take multiple ribbon stacks and put those multiple ribbon stacks in a cable. And man, we can get some tremendous density, high density fiber optics in the world of cables now, with multiple ribbon stacks loosely configured inside a cable jacket. How big do they get now, Chris? They're pretty extensive.
A little over 9,000 fibers, what Sumitomo has right now for data center trunk cable.
Right. And here's a picture of, there's a little picture here of a 12 ribbon fiber cable, and you can see the ribbons stacked together on top of each other. They're in a filled buffer tube. And then you can see the different elements across here that make up that cable. So this is the typical construction of an outside plant cable right here. And as Chris indicated, as more density is required in these very, very large data centers to move from one building to the other, or one bay to the other, or whatever, we need more and more fibers in a single cable just to reduce the labor to pull this fiber from one end to the other. So we're finding multiple ribbon stacks and cables now. So it's a very interesting thing about this ribbon cable. And for those of us that grew up in the premise world, and we grew up in 10 or 15 years ago, we never thought we would ever be using this kind of cable construction inside a data center, but we are today. And as we move from and this is one of the reasons we're doing this class, is as we move from multimode to single mode, and single mode becomes more prevalent inside the premise world, we need to know a little bit more about it. So those are all great questions, and they're very appropriate. All right, so let's move around. We were talking about these different types of cables. Here's a little chart that was put together. It shows our multimode cables that went from OM1, which was 62.5, to the next OM2, 3, 4, and 5, which are all 50 micron cables. And we can get to talk about all the different columns here, but typically the OM1 was considered a LAN cable. The OM2 cable, when we went to 50 micron, we wanted to move up to gigabit Ethernet, and that's when that came about. And then we wanted to get more applications. So we have 2,000 megahertz modal bandwidth to 4,700 modal bandwidth. And then we come up with some optimized multimode fiber that we can do some wave division multiplexing on right here that we call OM5. So the most popular cables in the world that we live in are OM3 and OM4. Is OM5 going to make it? I don't know. We'll talk about that in a different class. OM1 and OM2 are pretty much obsolete. They still exist, but for new construction, you probably won't be able to buy them for new construction, but there are elements of this available so you can do your Mac work. If we go to single mode fiber, there's two versions of that, OS1 and OS2. There's a new single mode fiber that came about, I guess it came about in the very late 2000s, like 2007, 2009, somewhere around in there, we came up with a new single mode fiber that was called OS2 that was bend insensitive. Well, maybe it was even older than that. But we came up with this bend insensitive fiber that we call outside OS single mode, outside plant single mode 2. That's the most prevalent cable right now today in the outside plant world. And we're going to find that the OS1 cable is pretty much obsolete. And these should be backwards compatible, so I could attach one to the other and they would still work. There is bend insensitive cable that allows me to make allow me to create a tighter bend in a cable in the multimode world. So you will find a bend insensitive fiber that will allow me to make a smaller loop in the fiber. I don't know whether you're not going to be able to get to a complete micro bend. You're not going to be able to fold it in half, but you can get that loop very, very small now with multimode using bend insensitive techniques that are used during construction, so that the angle at which the light goes through the core is not so close to 90 degrees that the light leaks all the way out into the clad. The goal is to keep all the light into the core, but if you overbend the cable, some of the signal will leak into the clad, and as a result of that, you're going to lose performance on the cable. So bend insensitive, as you see it down here in the lower right, is inside the multimode world these days. If you're buying Hubbell cable, I can tell you for sure that almost all of our multimode cable that's used for distribution cables and even some of our outside plant cables are all bend insensitive, if not all of them.
That's correct. And Carl, one comment, the losses that you show in this table are industry standard or Hubbell spec, which is greater than industry standard.
This is industry stuff. This isn't Hubbell stuff, I believe.
Yes, that's correct. Yeah.
That's what I thought. All right. We were talking about the different types of Ethernet in terms of range, etc. This is some of this has to do with what we were talking about, transceivers. But here I wanted to describe the difference between OM3, OM4, and OM5 and get to the point about how big the distance is in here. We use optical fiber in these worlds from 10 gigabit Ethernet all the way to 100 gigabit Ethernet, and our distances in OM3 and OM4, man, they get pretty long. I mean, they get up to 100 meters. So this is all important stuff when we're talking about fiber distance and how important it is. And we're going to get into what do all these numbers mean, and what does this syntax, what does this mean over here? We'll talk about that in another class. My point is all about distance. We have a much longer reach with fiber than we do with copper. So multimode fiber 62.5 and 50 micron, OM1 and OM2, they're no longer recommended in the standards. And OM1 is being replaced by OM2. And so OM1 is considered, and OM2 are considered legacy. They're considered legacy. So let's get to the color code. We were talking about the color code on these cables. So the color code's the same whether we're talking about ribbon cable or loose tube cable or tight buffered. So let's look at the color on the left. These are the colors of the individual fibers or the individual buffer tubes. It could be either one, whether it's tight buffered or whether it's a tube, it doesn't make any difference. The color code is the same. A blue tube at one end is going to hold all the fibers that are in a blue tube at the other end. A green tube is going to hold all the fibers at one end that are in an orange tube is going to be the same at the other end. So the color codes are the same. If this was a ribbon cable, we would have 12 different inked colored fibers laid down side by side in that schedule like we showed on the previous slide, and then they would be stacked up together and they would be put in a tube, And then if multiple tubes were put together, they would have the same color code, so we could keep the tubes separated. So if you think about this a little bit, the fiber has a color on it, and then the buffer has a color on it. And then what happens is that we jacket it, and then the jackets have a color on it. And so on the right, we have the color for the jackets of our cables. So OM1 is and OM2, which are legacy, they ended up being orange and gray. So if you're doing Mac work and you see an orange fiber optic cable, you better look at it real close to find out whether it's OM1 or OM2. You have to read the jacket because some OM2 cable might be orange. The same thing applies to OM3 and OM4. The standard practice is OM3 and OM4 would be aqua, an aqua color. But there's a new color that's come about. So we see people using violet for OM4. So my point to you all is when you're working with fiber and you come across an aqua cable, look at the jacket to see what it is. Is it OM3 or OM4? You could have, it could be different than what you think it is because there's this new introduction of violet into the jacket color of optical fiber cables for multimode. OM5 is green, and OS1 and OS2 outside plant cables are yellow for the outer jackets. So individual fibers are color coded. Individual buffers for tight buffered, they're color coded. And then buffer tubes are color coded. Does that, I know that might be a little complicated here. I tried to make it as easy as I could here. But if you have any questions about this, it's outlined in the standards and you can take a look at it. And of course, Chris and I will be here to help you with that. Are there any questions about this color code in the chat, Chris?
No questions about the color code yet.
All right, good.
There's still a little discussion about OSP, tight buffer, and loose tube. And I think as we get into the cables coming up, we'll clarify a couple of those questions.
All right. Yeah, I got to move along here. We're going to run out of time. So anyway, this is what the cable construction looks like. So I've given you a couple examples of it here. We have the individual fibers, and then in order to construct the cable, these are buffered or they're not. This is a buffer tube, but there could be multiple fibers inside this buffer tube, like shown here. So you have a buffer tube. In between the buffer tube and the individual fibers, you'll see some aramid yarn that adds strength to that cable. As we move down the cable, you're going to see that there's a strength member in the cable. It's a hard plastic that runs down the middle of the cable to give it some strength. All these cable elements are combined together, and we put some more aramid yarn or Kevlar in there again to strengthen it and to fill up the gaps. If it's a cable that's going to be in the ground, you'll find modern cables are using water blocking tape to absorb water so we can protect the fiber. And you would say, well, water won't hurt the fiber, and you're right, unless it freezes, and then it will. So if water gets into an outside plant cable and it freezes, you could put a micro bend into the fiber, and then it won't transmit at the same power that it was when it was launched into the cable. So water blocking tape absorbs that to keep that from happening. Then we jacket the cable. So we put a jacket then over the elements of the cable. And then in some cases, we may armor the cable, like you can see right here, and then there'll be another outer jacket. So this is a typical fiber construction. Now, that's not to say that all fibers are going to be put together this way. This is just an example. This world of how we're going to build a cable is changing very quickly. Chris has been involved with a lot of this as manufacturers continue to make these fibers, cables, the smallest diameter possible.
Correct.
Any questions about that, about how they're constructed? We'll move on then to the connectors. These are the common connectors we see today. We know there are others. The most common connector that you see up here is the LC. LC, I remember that. It equals a Lucent connector. It was kind of developed by Bell Labs. It's half the size. If you take the mass of this connector and compare it to an SC, Sam Charlie, or a subscriber connector, a standard connector, you're going to see the LC is much smaller than the SC. So as we move to high density connectors, so we can get more cables into a spot, you're going to see the LC is the most prevalent. STs are going away very rapidly. That was a bayonet. That's where you push the fiber onto a chassis mounted connector and you twist it a quarter turn to lock it into place. That was the ST connector. And then the newest connector for us that's going to become very important to us in the enterprise world is the MPO. And that's a multi-fiber push-off connector, an MPO. It's also known as an MTP. That's the trademark name for this cable. It was developed by Nippon Telephone in Japan. They invented the connector, the MPO. It's the most important connector for us coming into our future, the LC and the MPO.
Carl, the question came up, what about biconic connectors for us old timers?
I can't remember the last time I saw a biconic connector. That's how important it is. I don't know. There may be in the world of central offices and stuff like that. There could be some equipment out there with biconic connectors on it, but let's face it, in what we do every day, 99.9% of everything we're going to do anymore is going to be LCs and MPOs, in my opinion. And there's going to be some SCs scattered in there.
Yep.
All right. We were talking about these cable constructions. This is just out of a Hubbell catalog. And we do have the cable performance and the color references in there if you need to know that. And it does outline that all of our cables in these groups our distribution cables here are all bend insensitive, and it shows up on the spec page, and you can see it in the Hubbell catalog. Your Hubbell rep can help you with all of this. And we talk a little bit more about color coding on those spec sheets, so we're very clear about what our cables are going to look like. So these are
one more question on connectors. Does the military work still require ST style connector? And I'm not familiar with the current mil standard.
I'm sure there's military equipment that uses STs. Now, does the military use LCs and SCs? I don't know. I really don't know. I am sure they are. Now, maybe there's something where you're on an aircraft and there's fiber on an aircraft and they're afraid that vibration may cause this to come out and they want this lock feature on there, and you could find some STs. Just understand that the more fiber you put in, the more STs you put in, the bigger the equipment's going to be. It's going to take up more real estate. But I really can't answer that. I'm not a government military spec expert by any means, so I don't know. We could look it up for you. We'll try to find the answer for you. If you put the question up there, we'll get back to you on that.
And another question while we're on connectors, what about the new SN connector from Cinco, smaller than LC for high density data centers?
It does exist. We're not addressing that in our sessions that we're doing on these four that we're doing, but we do address it in our standards presentations that we do around the country, and we do know that that connector's coming our way. We're very cognizant of the fact of these new connectors. Just understand this. I doubt very seriously whether the standards people are going to standardize on one. They're going to let the market prevail just like they do on these connectors.
Yeah. And also another question from Scott Agent is, do you think APCs, angled pouch connectors, will become more popular in the connector world?
Yeah, they will, especially as we increase our speed and more need for single mode fiber. I don't know whether it's going to become prevalent in the world of multimode, but in single mode for sure. Single mode's coming our way.
And one more comment from Trevor Platt. For many legacy military installs, they're still using ST. For newer installs and new builds, we see keyed LC systems.
Yeah.
There you go. That's a good answer from Trevor. Thank you very much.
I know that. So.
All right, please mute if you're not muted.
I think that's Brian that's not muted.
We have 10,000 feet in stock in Joliet. Okay.
I'm trying to.
Brian, you need to mute yourself.
Please mute.
Thank you. All right. These are typical cable constructions that you'll find. They could be single mode or multi-mode. We're showing you single mode OS2 over here and OM1 over here. This is a typical duplex connector right here. It's a pretty common thing where one cable is used for transmit, one's cable is used for receive, or one fiber's for transmit and one's for receive. And it's available to you indoor, Plenum and riser. Pretty common stuff in the enterprise world. And then we move to multi-unit cables or tight buffered constructed cables, and they're very common. They come in subunits of 6 or 12. So if you want to get a 72 strand multi-unit cable like this in either OM3, OM4, or single mode, you typically have 6 12 fiber subunits. So 6 times 12 would come up with 72 fibers, which is pretty common. Chris, I think there's some other subunits that are becoming popular. Are they not 612? Are there others?
There's a base 8 standard that you'll see that they're using where you have subunits of 8. And they're referring to it as base 8 cable, yes.
Yeah. So if you look at this, each one of these buffers, right, buffer tubes right here is a subunit. And then they have the number of fibers that are inside the subunit. So let's take a look at this OM4. We have 1, 2, 3, 4, 5, 6 subunits, and inside each subunit there are 12 fibers to equal 72. That's how the math works. But what we're talking about is these subunits here for these individual buffer tubes. They can vary. And 8's becoming a number that's going to become important to us. And then we look at indoor-outdoor cables that can move in both places. These are very good to know when you're going from one building to another, and you're going to run a cable in a conduit, plastic pipe or something from one building to the next, or you have some outdoor equipment that has to come into the building. It's nice to know that you have this stuff available to you. OM1, OM2, OM4, OS2, Plenum and riser, and you can get it in the same construction, indoor, outdoor, that you can get for indoor. Here's some more indoor, outdoor tight buffered. So these go in both directions, indoor, outdoor. One thing I'll point out, if you're bringing an outdoor cable indoors, be very careful. This one just happens to be Plenum and riser rated right here, so you can use it in damp spots, lay it on the floor and stuff like that. But you can get to some where it's only outdoor, and you got to be careful how you terminate that and where you terminate it inside a building. But the point is, there's lots of different types of constructions for different purposes, just like we talked about before. So these are 72 fibers, available up to 72 fibers in Plenum and riser, both single mode and multi-mode. Here's an indoor-outdoor riser cable, standard riser with a PVC jacket. Indoor-outdoor riser. And you can get that up to 72 strands. And on single mode, you can get it all the way up to 144. Then we have one that's Plenum. This is a new one for us. So rather than just being riser, we have an indoor-outdoor Plenum cable available for you too, all the way up to 144 strands with single mode, up to 72 strands with multi-mode. This is the one I was warning you about. If you get this kind of cable, it's an outside plant only and it's not rated, it won't be fire rated. You have to terminate this within 50 feet, I believe, if you bring it inside a building to meet code. You can't take this and bring it in and then move it right on into the building. You have to make a transition from the outside plant cable to the proper indoor cable in a certain amount of space that's going to be written in the codes and standards, and your AHJ is probably going to know the answer to that question, but we can help you with it too if you want to call us and find out. Armored, the only thing I want to say about armored cable is this armor right here does not help you with backhoes. So if you have a backhoe cut and you say, well, it was armored cable, it doesn't mean anything. This armor is put on these cables to protect that cable from rodents. And in some cases, if it's aerial, it could protect it from shotgun shells or that kind of thing, people shooting at the cable with a shotgun, but it's not going to protect you. Armored cable is not going to protect you from a backhoe. It's designed to protect the cable from rodents. So that's the end of it, Chris. For those that are online, Chris is going to put a he's going to put a link into your into the chat, and we're going to stay online with you here for a little bit, maybe about 5 minutes or so, 4 minutes or so, and give you an opportunity to fill out that form. When you click on that link, fill out the form and hit submit, and that will get you your BICSI certificate.
Yes, and I just put the form, the link to the certificate completion form into the chat, and I also added in there our email address if you'd like to email us and get a copy of the presentation. We've got a couple of comments from Mike Heinsohn. Is those backhoes keep OSP companies in business? That's
yes,
absolutely
they do. That's a good thing. We love backhoes, right?
People that dig before they call often dig up fiber cable, as we know. Michael Broomberg, can the outdoor fiber cables be specified with an integral copper cable for tracing? Yes, there are cables that can be specified to have either a specific armor that can be used for tracing, or a copper trace wire, like two 22 gauge wires, a pair that can be used for tracing as well.
Some people put a metallic tape in the trench before they backfill too.
That as well, yes.
Yeah.
And Andrew Pagano said, I would add that for armored cable, be aware of the bend radius. Absolutely. Be aware of bend radius for armored cable, and twisting. It may be different depending on the whose product you buy. It may have a different specified bend radius. And never violate bend radius.
No, don't violate bend radius. Right.
Okay, we're getting quite a bit of feedback on getting a copy of the presentation, and we'll reach out to you with that. But please be sure to go to the link. I'll post just the link again here in just a minute, so it's fresh in the feed. But go to that link and fill that out so we know that who was here, and we can provide a certificate.
I would like to see some of y'all come back to our session number 2 next Thursday at the same time. Same time, same place next Thursday, and we'll dig in a little bit deeper in fiber optic number 2. And we'll get a little bit closer to all those questions about transceivers and that kind of stuff.
Okay. Let me make sure if I can.
You're welcome, Scott. You
make
too,
sure
John.
I'll work out any other questions here versus okay. Any other questions? Please pop them in there while we've got Carl's attention. And otherwise, please, put your email address in there, and we'll shoot you the presentation. Getting quite a lot of responses there, Carl. So
I've already got it. I have it prepared in a PDF, and I can send it out. All I need to do is compile all the email addresses.
very good. And I'll get that here short. I'm going to post the link again. The link flowed by in the chat. Here it comes again. You may have to scroll up to see it in a minute if you don't click on that link soon. You can copy and paste that link out. If for some reason you missed that, you can reach me. My email address in there as well, but that'll fly by also. So
I see there's somebody asked for the link again at 2:08.
Yeah, I'm posting it.
Oh, there it is. It came up just now, whoever asked for the link.
Yeah.
So Jim Lumen, look on your chat. You'll find Jim Lumen. Look in the chat at the scroll down toward the bottom and you'll see it. He just posted it at 2:09.
Yeah, you may have to scroll up, and I'll keep posting it as long as there's activity here.
All right, We're going to give you another.
I don't see a thing. What you're talking about, a link? I'm scrolling. I don't have.
You got chat. You got a little on Teams. You have a little button there that looks like a.
I think, Carl, they may be on the phone.
Oh. Oh yeah. If you're just on your cell phone, you're not going to.
No, I'm on Teams. I don't see a chat.
Put your cursor all the way up toward the top of the screen, and you'll see a little window will pop open, and you'll see what's representative of a conversation. It's one of those little globes with a point on it for chat. And then when you get into that chat window, it'll show up on the right, and you can scroll down or up and get to the link. You still having a problem?
Yeah, I'm not getting any chat. I'm familiar with Teams. I don't have it. It's not there.
Did you push your cursor all the way up to the top of the screen?
Yes, sir. Nothing happens.
I wonder why that is. You should have it. Would you do me a favor? Just put a note in the chat. Can you see it? You don't even see chat at all.
I don't even see chat. No.
All right. Well, we can help you with that. Give me your email address right now.
Sure. It's swheeler, WHEELER @jdrm.com.
G as in George, E.
No, J D as in dog, RM.com. So swheeler, WHEELER @jdrm.com.
Is your first name Scott?
Steve.
No. I thought I knew a Scott Wheeler at one time. Okay. swheeler@jdrm.com, and I will make sure you get your cert.
Thanks.
And I'll also send you a PDF of the presentation.
Appreciate it. Sorry.
Not a problem.
We've got another question from Ron Ostendorf about planning on a 144 fiber cable. What was the diameter? Ron, that's going to come down to which type of product if you're using a tight buffer, say Plenum or riser, or whether you're going to use an interlock armor cable, the diameter is going to change quite a bit.
Can you send that link to everybody for the certificate?
Well, we have a mechanism. We have a mechanism using chat. Can you get the chat? Do you know how to open the chat window in Teams?
No, cannot get the chat.
The preferred method to get the certificate is to open the link in chat. Have you moved your cursor all the way to the top of the screen?
Oh yeah. I moved it all the way up. No chat anywhere.
All right, give me your email address.
D Fitzpatrick.
FITZ.
It's ZPATRICK.
At.
FE Moran.
Would you spell that out for me?
FE Moran, MORAN.
FEMORAN.
No, yes.
Okay, let me make sure I got this. D Fitzpatrick at F as in Frank, E as in Ethel, Moran, MORAN.com.
It's security.com.
Oh, okay. FE Moran Security.com. Yep. Okay, I'll make sure that you get a certificate.
Okay, thank you,
Mr. Fitzpatrick. All others, please hit the link in chat. And if you don't have a question and you've hit the link in chat and you filled out the form, you're okay to go. We're done. And then we'll keep an eye on the screen here, and we'll kill it in a little bit. You guys can go ahead and leave. You ladies and men can go ahead and leave whenever you like if you're no longer asking a question or you've already requested a certificate.
Now, just out of curiosity, I'm doing this on my phone because I'm mobile right now and I'm not sitting at a laptop now. I've already filled out the information, so the email will come back to me.
Yeah. If you'll look in your,
okay.
What'll happen is you'll get your certificate in a couple of days. The information on that form goes up to corporate marketing. They prepared a certificate, so they'll take it off the spreadsheet. They'll drop it into your cert. They'll print the certs and then they'll email them to you.
Okay, sounds good. And tell you what, man, I'm new to the field, and I appreciate all the knowledge that I can get from you guys.
All right.
The more
Well,
the better. So
yeah, join us for the next 3 sessions, and by the end of it, you'll be on your way in the world of fiber.
yes, sir. I've already registered for the other 3, so I'll be looking forward to hearing from you guys.
Well,
Again.
we're glad for your comment. Thank you very much. That that makes us feel good that we hit a need out there.
Most definitely, man. I appreciate it. Thank you, guys.
You bet.
Certainly.
You guys have a good evening.
You do too. And Ron, I'm getting you an answer. Ron Ostendorf, hang on just a minute and I'll have you an answer. So Ron, that cable's going to be about 19.28 millimeters, which comes in at about 3/4 inches. It comes in just over 3/4 of an inch. I'll put it in the chat in case you can't hear me.
Well, when you think you're getting 144 cables, or 144 fibers in this is an outside plant cable, 144 fibers armored.
This is a Plenum. This is a Plenum indoor interlock.
Oh, Plenum. Okay. All right. Got it. It's still a pretty small cable for what you're getting.
That is for an indoor cable. But in the case, I mean, if you see what's available these days with like the 864 micro airblown cable, you know, which comes in, you can put it in a 1-inch duct. So it has to come in at around 0.65 inches. So,
Yep.
All right.
All right. We're going to give you all 1 more minute and then we're going to close it up. We're assuming that the people that have not left the chat have left the room and they're not listening to us.
They've left the building. Carl, give me a call afterwards if you would.
All right, I'm gonna shut this thing down in 1 minute.
Thank you, everybody, for attending today. We look forward to seeing you next week.
Thank you.
Have a great and safe week and weekend.